We will begin this module with the review of the topics that we have done so far, and today we are going to talk about a new topic which is called packages in general, and we look at various formats of packages and try to understand what benefits you get by using different formats of packages and under what applications you can use each of these. So, the selection of packages in your future design work and applications require you to understand the various cross sections of packages and understand the inside of packages, so that you can utilize to the maximum benefit the electrical characteristics that are embedded in these packages. So, we will begin with a review of the topics that we have done so far. What we have seen is levels of packaging. We have seen first, second and third level of packaging and understood the critical areas in each of these levels of packaging. Secondly, we saw what is the definition of a product, a system. We have defined what packaging is, and we have seen at least 4 different case studies of systems packaging. Then we have looked at roadmaps. Initially, we looked at the semiconductor roadmap. We also had a brief glimpse about the packaging and assembly roadmap. And I need not emphasize here that roadmaps are very critical in understanding the growth of the packaging industry. I hope by now you are aware of the usefulness of various roadmaps. I have to remind you that even industries have roadmaps. Even industries that manufacture packages have certain roadmaps, and they work according to those timelines. Then we saw what a semiconductor wafer fab is and how the processes in this particular industry have grown over the decades. We have also seen flow chart of the front end and back end processes, and we have seen the criticality of various process steps in defining a particular technology and therefore, the growth in the semiconductor industry. Then we have seen the first level connection choices. What are those connection choices? Wire bond, tab and flip chip. So, we have seen exhaustively and extensively what a wire bond means, what are the materials used in wire bond, how the process is established, and then we have seen tab, tape automated bonding, the areas of application for tab and the methodology of connection in tab, especially the inner lead bond and the outer lead bond, which by now you are familiar with. And then we looked at C4, that is the flip chip process, which is currently very popular, and we are going to see how flip chip methodology of interconnection or chip connection choice is utilized in fabricating or bringing out these packages. Today, we are going to look at packages in general, and we look at package form factors. We look at the suitability of packages for second level interconnection. I hope by now you are aware of what is a second level interconnection. The second level interconnection means your package is now connected to a printed wiring board. The printed wiring board is a system level printed wiring board, because a printed wiring board by itself can perform system functions. It is highly integrated, it is a high density board, and you can pack as many components as you would like, because the technology growth in the second level is enormous, and we have to fully utilize those technologies, so that the package that you are using becomes by itself added advantage in terms of density in the second level interconnect system. So, we will now look at the packages. What do you mean by packages? Broadly, we can define packages as single chip package or single chip packages, or another term used today is single chip modules. You call it as SCM. Sometimes this acronym called SCP is used. So, whenever you look at this acronym in the packaging context, you can identify them as single chip packages or single chip modules. Okay. Now, you have the other end, that is multi chip packages or multi chip modules. So, you might also hear the term called multi chip packaging, which basically describes the process sequences in building a multi chip package. So, the criteria for forming a single chip module and a multi chip module are completely different. So, what we are trying to understand through this chapter is that, as the name indicates, a single chip package will contain one chip or one die interconnected in a suitable format and then packaged. Packaged means it is protected from the external environment and other external factors like temperature, humidity, dust and so on, and including electrical and thermal effects. Then, as the name indicates, multi-chip modules or multi-chip package, it means that that package will have two or more die interconnected on the same substrate. So, the first time definition for single chip package and multi-chip module or multi-chip package basically gives you an indicator that how many dies are present in the package form. So, we will try to define further what is a single chip package. A single chip package is a package that supports one microelectronic device, so that its electrical, mechanical, thermal and chemical performance are adequately served. So, it is not enough that we take a platform of a base platform like a substrate. It can be an organic substrate or a ceramic substrate or some other substrate that is suited for that application, but then you have to look at how to fan out the IOs from that single die suitably, so that as per your design the electrical characteristics are not diminished, it has got better mechanical and thermal properties, and the chemical performance in terms of its interaction of the materials with the environment is not changed, it is adequately served. So, the device originates from a wafer. So, the starting point, as you can see in this picture, is the wafer. We started with a wafer. Then after the wafer is totally tested and the process completed, we are now singulating the dies from the wafer. So, you get a known good die. So, this is the die. You can perform the required electrical tests and then call it as a known good die, KGD. Then it is packaged, and then again after the packaging is done, it is burnt in using several standards based on the materials that you are using, tested and then qualified to be sent to the market. So, such a packaged die or IC may contain millions of transistors or integrated circuits. So, basically if you can look at a microprocessor application, the die is singulated, then it is packaged, and then we are going to look at what format or form this particular microprocessor die is going to be available in the market, whether it is going to be in the form of a lead or a pin or a solder ball, okay? Or normally for microprocessors it is going to be packaged, but for other prototyping applications this packaging sometimes may not be done. So, it can directly be mounted onto your second level system, which is the printed wiring board. So, that is known as a bare die. So, the conditions for using a bare die and a packaged die depends on the application that you are going to work with. So, but normally it is preferred to have a well packaged IC to be used for high end applications. Now, as you can see from the wafer, the die is singulated and then it goes into the process that we talked about, wire bonding or tab or a flip chip. In this particular picture, what you are seeing here is a wire bond, and then these are the lead frames, and then you can see the bare die at the center resting on a substrate. At this particular point, we are going to do a die bonding, and that is how it is resting on that particular base of the lead frame material. Then you can see the wire bond or the first level interconnection is attached to the lead frame, and then it is packaged or encapsulated. So, you have to choose a suitable encapsulant and then mold the material, so that you get a well defined thickness of the plastic material, and as per quality you can check the thickness, the length of the lead frame and so on, and then send it into the market. So, wafer to single die to a packaged die. Then you can see here, this is how a single chip package or a single chip module will look like. Here you can see at the center there is the encapsulant material. If you rip open this particular package, you will see the bare die inside. So, here the die is protected, and along the periphery you can see the interconnections or the IOs brought out from the die. So, typically this is a package that you would have used, and this is known as a quad flat pack, for example QFP. Q because it is a quad interconnection, the IOs are at the periphery and at the four sides of the die. So, because of this you are able to increase the number of IOs, right, or it can be in the form of this particular format. This is different from the QFP. This is known as a pin grid array, PGA. So, for example, Intel's microprocessors recently have been in the format of pin grid array, PGA. So, here you can see the interconnections are in the form of pins. These are the pins which will get attached to your system level printed wiring board. So, various companies like Intel also bring out their microprocessors in a PGA format. Some of them will bring in a ball grid array format, and some others in a QFP format. That depends on the number of IOs and also the pitch. I hope you remember what a pitch is, and then pitch is going to be a very crucial decisive factor in determining and custom building your format for the IC packages, because you are going to make it, the industries are going to make it in millions. So, they have to consider cost, the materials, the number of IOs and the pitch to decide on what kind of package they can finally bring out for that particular design. So, what are the functions of a single chip package? Firstly, it provides an efficient means for signal transmission and power distribution to and from the IC, from which you are going to take the IOs and then you are packaging it later. We have seen this particular statement in the definition for packaging, if you recollect. So, whenever you look at a package, we are not really worried simply at the number of IOs. The IOs and the package format will finally be converted into some methodology for efficient means of signal transmission without loss in signal, which means the signal propagation delay should be very low. You would have calculated something from your circuit design regarding the signal propagation delay, but when you use the package, it should not be lowered to a great extent. Agreed that the package will contribute to some extent in the delay or loss, but we have to make sure that the tolerance levels are minimum. Power distribution, very important for the working of the IC, and that depends on the power that you have calculated for running the IC without a package, and with the package you have to basically do some testing before these packages are sent to the market. These packages will have to provide an efficient means for signal transmission and power distribution between the packaged device and then the other components that you are going to mount on the system level printed wiring board, because an IC is not going to perform by itself. The performance is related to the other subsystems. It can mean a number of capacitors and resistors, inductors, electromechanical devices, other integrated circuits or active devices that you are mounting on that system level board, and on that particular device you are going to interconnect these various active devices and passive devices to perform a particular system function. It can be an analog function, it can be a digital or mixed signal, high bandwidth, and so on. So, it can be a high power application circuit. So, depending on the type of application, your IC has to perform efficiently in this mixed environment. Thirdly, the package has to enable the device to be attached to the next level of packaging through a suitable interconnect scheme, such as a surface mount technology, which I talked about briefly. You now know what is a through hole technology component and a surface mount technology component. Today, the surface mount technology is growing leaps and bounds, and most packages are being available in the surface mount technology format. Then the package should allow for efficient and effective dissipation of heat when the package is powered up, right. So, when the package is powered up through the circuit that you have designed, there will be heat generated from the device, from the active device. And how are you going to take care of it? Partly the package material has to take care of to dissipate the heat from the silicon die through the package material to the environment, and that happens through the system level printed wiring board. And if you are an efficient designer of the printed wiring board, you will take care of heat in different ways through the solder joint, through some kind of a heat sink or a copper plane that you have generated in the printed wiring board to remove the heat quickly. Other methods can be by using an external heat sink on top of the device to efficiently remove the heat. So, this is a very important point that you have to take care of in deciding what package you want to use. So, I would put this as a very important point of discussion. The fifth point is the package should provide adequate protection of the device in concern, basically the silicon device, from external forces of mechanical or environmental nature which may damage the device. So, obviously, when you look at any package, depending upon the size, the package volume also increases. The package volume and the package material, therefore, will have to take care of temperature changes, moisture changes in the particular area of operation of the device, and then dust, and then finally other electrical or other mechanical interruptions like vibration or a shock and so on. Then finally, the device should act as a space transformer between the fine pitch grid of IC. Please note this point very carefully, because we are talking about two levels of pitch here. At the IC end, typically for example, it could be 100 micron pitch, and at the system level printed wiring board end, it could be around 200 micron range pitch. So, we are talking about this space transformation from 100 to 200 microns. So, your substrate is going to handle this space transformation between the device and the board. How do you take care of this? Because you cannot handle fine pitch at the system level currently because of the limitations in technologies and the assembly limitations, but you are going to establish that in your package by having a suitable fan out. This is typical of your ball grid arrays, which you are going to see later, how efficiently the substrate takes care of space transformation between two types of pitches. One is a fine pitch and one is a fairly larger pitch that you can probably handle, and this is the type of pitch that you will utilize for mounting your substrates on the printed wiring board. What are the types of single chip packages that are available? They can be classified based on package materials. First thing, it can be a plastic package. The second thing, it can be a thin film or a tape carrier, and thirdly, it can be a ceramic material that can be used to package the material, which means in the first case you are going to use a plastic substrate. In this case, you are going to have the IOs in a thin film mode or a tape, example polyimide, and thirdly, it can be a ceramic substrate that can be used for packaging your device. The other classification is based on IC assembly type. So, it can be a surface mount device, it can be a through hole device, or it can be a direct chip attach. I want you to turn your attention to this particular samples that are given here, where I will try to show you on this classification. For example, this is a plastic package, okay. Then this is a ceramic package, that means the substrates for each of these are different. Then if you look at this particular device, this is a quad flat pack, this is of surface mount technology. Then we have this one, this is a dual inline pack, which is a plated through hole technology, because they have long leads which go into the holes of the printed wiring board. And then if you look at direct chip attach, for example, this is a bare die which can be considered as a flip chip, and can be directly attached to your printed wiring board. So, the pitch here is going to be very small compared to the pitch here and here. So, the assembly techniques also define the types of single packages, single chip packages, and finally, the classification is based on IC interconnections. It can be quad flat pack, it can be partial area array, or it can be a complete area array package. Okay. So, you know what is a quad flat pack, which means the die is here and the leads are taken from the four sides. There are different types in a quad flat pack. Then if it is a partial area array, that means the die is here and you are going to utilize partly at the back side of the die or the package by using solder balls. This is a BGA connection, but a complete area array would mean the entire area under the die is utilized for creating solder balls. This is also a BGA. So, that depends on the size of the die, the pitch, and the amount of heat that is dissipated. Okay. So, these are the basic types of single chip packages that you will encounter. If you look at this figure, on one side you see peripheral packages, on the other side you see area array packages. In the peripheral packages, we have moved from dip to plastic dip packages. Then we have seen the growth of PLCCs, plastic leaded chip carriers, small outline integrated circuits. This number that is written here denotes the pitch of the component. 1.27 mm is the pitch of the package. Then we move to a smaller pitch 0.65 mm for PQFP, which is plastic quad flat pack. Then we have worked with 0.5 mm plastic quad flat pack, 0.4 mm PQFP, 0.3 mm QFP, which means we have seen that the pitch has reduced continuously over a period of time. Okay. So, we are at 2010, 2011 today, and we have seen the growth. Lower pitches means growth, or high density packages are being utilized or produced by the industry. Okay. Then we have area array packages on the other side. Pin grid array packages typically used for Intel microprocessors and other companies which have utilized PGAs. Initially they were ceramic because the number of IOs were very large. Then it has gone into plastic PGAs. Then we have moved to ball grid arrays. PGAs are similar to BGA. The only thing is, in BGAs the pins are replaced by solder balls. So, in BGA, for example, initially during 80 to 90 we have worked with 1.5 mm pitch ball grid arrays. Then 1.27 mm became a good standard plastic ball grid array, 1 mm, 0.8 mm, and today we are working at 0.65 ball grid arrays. And then what next? Then if you look at the other extremities, direct chip attached to printed wiring board. Okay. Typically you can call it as a flip chip or a chip on board technology, which I have briefly mentioned in the earlier class. So, DCA, direct chip attached with a pitch of 1.5 mm, 1 mm, and now what next? Flip chip to ceramic, 3 mm, 2 mm, 1 mm, 0.8 mm, and what next? So, all of these technologies that we have seen very high growth rate in terms of lowering of pitch has now culminated in a very new technology called chip size package or chip scale package, or it can also be known as wafer level CSP. Now, if you look at the pitch here, CSP is classified if the pitch is 0.5 mm or below. Otherwise, you can call it as a plastic ball grid array or a ceramic ball grid array, or a PQFP with a 0.3 mm we have seen. But if you look at CSP, the definition or the qualification for a BGA package to be called as a CSP is the pitch should be 0.5 mm or lower. Today there are new technologies called wafer level chip size packaging, which has got pitch as low as 100 microns, that is 0.1 mm. As you know, the CSP methodology and wafer level CSP methodologies are slightly different. I will briefly explain about conventional CSP and wafer level CSP shortly. But the BGA and CSP, the difference you have to know, the basic difference here is that the package volume is much less in a CSP compared to a BGA. So, today we are in the era of CSPs. If you look at this particular slide, which talks about packaging efficiency on one side and then the timeline. Okay. This is a slightly outdated figure, but nevertheless it holds very good, because we need to know how the evolution has taken place in terms of efficiency. So, if you look at efficiency of package or package efficiency, it is IC size by package size. Obviously, in a DIP package, the package size is very large compared to the IC size. That is why in a DIP package the efficiency is low. So, the efficiency increased slowly through the PGA, through a BGA and then a CSP, and finally, at a CSP wafer level package, the efficiency is very high. So, if you have the different ends dip on one side and CSP on the other side, you can very clearly say that CSP has a very high packaging efficiency, because the package volume is much less in comparison to the die size in the CSP and compared to a dip package or a QFP. This particular graph or illustration will talk to you about connection density, that is the number of pins, number of IOs per package. So, if you look at the graph in terms of lead pitch, that is the distance between two adjacent pins in a package, that is the midpoint of the pin number 1 to the midpoint of the pin adjacent pin number 2, that is lead pitch. 2, connection density, that is number of leads per centimeter squared when you actually mount them or design them to be mounted onto a system level printed wiring board. So, you have dip package, which obviously the lead pitch is very large, therefore, the connection density is obviously lower, okay, compared to a ball grid array, where the lead pitch you can work as low as 0.5 mm. Therefore, the connection density when you use a number of area array packages replacing dip packages or a QFP package will give an increase in the connection density. And when you use a bare chip obviously or a 3D module, you can expect a multifold increase in the connection density. The best example is a CSP, which will have a better connection density compared to a even an area array package or a QFP package. If you look at the volumes of packages that have been produced globally, this picture will give you a very nice idea, because this is very current. If you look at the various colors that represent the various packages, and on the left side you see the volume in production in terms of billions of units, and here is the timeline going up to 2020. You will see that compared to 1980, today we are working at a large volume of surface mount in our circuit design. That means, the surface mount technology packages are coming out in large numbers in the market. You can see that the through holes represented by this color is totally diminished compared to 1980. You can see very few numbers are coming into the market. In the next 5 years and the next 10 years, you will probably see hardly any through hole components in the market, because all of them would have been converted into surface mount format, because the methodology of mounting and assembling surface mount devices are well known. The yields are very high, the throughput is very high. Therefore, people are opting for converting from through hole to surface mount. Then you can see absolutely large growth of flip chip, which was not at all there in the 1980s up to 1990. Then we talked about area array packages, which have a very high growth rate compared in the last 2 decades, that is BGA, CSP and pin grid arrays. Bare die, that is your chip on board process, is also catching up. As you know, if I am asking you to specify the application areas for chip on board, typically it will be for handheld applications. And then modified lead frame packages like quad flat no lead or micro lead frame packages are also increasing in terms of manufacturing numbers. So, you can see looking at this graph, the first thing that strikes you here is surface mount technology is very popular. Area array technologies are becoming popular and will continue for a long time. Bare dies utilized like flip chip or chip on board will continue to be used in prototyping and small volume category. So, this is what I meant by what a wafer level package is and what is a conventional IC package. In one of the classes you have seen through the video or some of the illustrations that the wafer is manufactured, it is singulated and then it is packaged. So, this is the conventional method of packaging a die, right. You create a wafer, you dice it and each die is tested and then it is packaged. That is how you get the different formats like a dip or a QFP. But a wafer level package is slightly different. The wafer is done, the packaging is done at the wafer level. That means, you are not singulating the die here, you are doing the packaging process on the wafer itself for each and every one of the qualified die and then you are singulating it. So, the singulation process is done after the individual ICs are packaged when it is at the wafer. So, what are the advantages? You can do away with a lot of cost budgeting, and there can be 10 to 50 times size reduction because you are doing it on the wafer. You will tend to add much less package material when it is on the wafer, and the manufacturing technologies for these are getting well established. But there is no single industry standard that exists today for wafer level packaging, because there are very few players in the global market for manufacturing wafer level packages. So, when you talk about wafer level package, essentially you are meaning you are going to create a CSP package, chip size package. That is the best thing that you can generate from a wafer level packaging. You are not talking about low density packages. So, the advantages of using a wafer level package will be power distribution with minimum noise and electromigration, because the interconnect lengths are very low, better signal integrity, that is better electrical performance, lead free solder bumping is possible. You can do this bumping process at the wafer itself and you can use lead free material. The interconnections are nano, as I mentioned earlier, that adds to better performance. And then these are ideal, chip size packages are very ideal for MEMS applications and MOEMS applications. And because this is not truly well understood today, because it is the monopoly of a very few industries, it integrates wafer fab, packaging, test and burn in all at the wafer level. Okay. So, I hope you get a very clear picture about what a conventional IC packaging is and what a wafer level package to produce a wafer level CSP is. Now, there are two types of interconnects you are familiar with. One is the wires, the other is the bump. You can see the die here and then you can see the first level interconnect done by wires. In this case, you can see the die here and the first level interconnect is done by a few solder bumps, and you can see the micrograph of the wires in this particular picture. You can see the row of wires that are attached by ball bonding, and on the right side you can see solder balls that are typically present in a ball grid array package or a CSP package. So, now the question that many people debate is, which is better, whether you need to use wires or bumps. So, wires have been there for a long time, right from the dip package to QFP, but as the size diminishes, using a wire bonding becomes a problem because of the height factor, the profile of the package. If it is going to be small, then you can look at utilizing solder bump technologies, which are much suited for low profile packages, small outline packages and CSPs. There are many other issues also in terms of electrical characteristics and thermal issues. Obviously, the package on the left is depicted as a BGA here. You can see the second level interconnect is a BGA. Here also it is a BGA, but here the first level interconnect is a bump and here the first level interconnect is a wire. So, this is the basic difference between these two. Okay. We are not going to consider here a wire and a lead frame, because typically that is low dense. These two options that I have presented here in this slide are typically high dense packages, because it is ball grid array which enables you to work at low pitch, but the first level interconnect here are varied. One is a wire, the other is a solder bump. So, the wires will obviously give you peripheral attachment, you can't do an area array attachment, whereas in the bump you can do a complete area array attachment. Obviously, the number of IOs here can be larger compared to the number of IOs that you can generate here. So, like this you can find out various benefits in terms of bare die in a solder bump format with a BGA compared to a wire with a BGA. So, again it depends on the number of IOs. Now, is it really required to use a package? A chip is useless without a package, as many people would like to affirm, because it gives you a much well defined methodology for system functions like power delivery to the chip efficiently through a much larger pitch and the interconnect device dimensions. You can utilize space transformer from the die to the package like a BGA or a QFP or a J bend lead frame and so on. So, transfers information into and out of the chip to the system level printed wiring board or the printed circuit board, draws heat away from the chip. So, the package plays a very important role in removing some element of the heat away from the chip, so that the die does not crack when it is powered up and if there is no sufficient cooling, and it protects the chip from outside elements. This is another slide that talks to you about the same point, that is chip package is a space transformer for chip to PCB interconnection. Now, if you look at the arrow here, this is typically for example an organic substrate that you can think about, a system level printed wiring board. Then you have again an organic substrate that could be used as a substrate material in the package. So, this part of it is known as the package, and this is your PWB, and this is the space transformation that you are talking about. Here this is the die and this is the bump that comes out from the die. So, you can see that this pitch is very small, a low pitch die. Then the IOs from the bump are space transformed through the multi layers of the IC package. So, you can imagine that this package is a multi-level organic substrate, multi-layered organic substrate, and through that your pitch has become large, right. So, you are able to fan out the low pitch at the die end to a larger pitch at the back of the package, that is typically this is a ball grid array package or it can be a CSP package. These are advanced packages, and you are able to handle this kind of a pitch. Let us say this is 0.5 mm or 0.3 mm. You are now able to handle this size of pitch when you look at technologies available to mount this particular device onto the printed wiring board and establish a second level interconnect. Okay. Now, when you look at such a system where you have a die and then you have an organic substrate for the die housing and then a printed wiring board, if you power up the circuit, this kind of a circuit for example, electrons start flowing from the die through the solder bump, through the multi-layer substrate to the BGA solder balls, what happens is a host of electrical, mechanical, thermal and materials issues get changed. We may not realize it. Firstly, when you power up the circuit, there is going to be a lot of electrical issues that come up, because we do not know what is the track width length, we do not know what is the dielectric constant of the organic substrate that you are using, and we also do not know what is the environment in which the package is going to be mounted, and what are the neighbors on the system level printed wiring board which will interfere in the electrical performance of this particular die. So, there can be issues like crosstalk, impedance issues and other electrical parasitics that you have to take care of, or which will become visible if you try to test these kind of electrical issues. Then we have mechanical issues. If you do not take care of thermal management, then typically your die can crack. Okay. This is a very important area where heat can play a major role. Your die can crack, your package can get warped, or your board surface and the solder joints can get affected due to thermal issues, or the thermomechanical reliability becomes a question. Mechanical issues like if you look at vibration or mechanical shock just by dropping, then there can be shocks that can be transformed to the solder bump or the solder joints at the PWB, which can result in a failure, electrical failure. And then materials issues. When you design a particular package for which a particular organic substrate is used, and then if you are going to use dielectric materials which are going to be conducive for the application, then you are saved. Otherwise, properties for these materials like dielectric constant, moisture absorption, the thermal coefficient of expansion, and another important thing called the glass transition temperature of the organic substrate, which we are going to see in detail when we come to PWB technologies, are going to play a major role in defining this system. If I call this as a system, all these 4 points, electrical, mechanical, thermal and material issues are going to play a major role. So, how does an IC package look like? When you open up a package and see, this shows a package that is typically removed of the epoxy material, a cross section, and you can see the molding compound on top, the lead frame. The lead frame here, there is a die attached at the center on a suitable substrate, which is attached by a die attach adhesive. Then you can see the wire bond and then the periphery of the lead frame. So, this is typically a inside of an IC, and this gives you a top view of the IC package. This is how the dip package, for example, will look like. These are the IO points that you are going to utilize to interconnect to your printed wiring board. This is the package material. This is the IO pad or the bond pad of the die. This is the die itself, and this is the cavity. Okay. So, there are different formats even for a dip package, which we will see shortly. So, why package ICs? Because pure silicon is actually difficult to handle, because the die is very fragile. It can be sensitive to the environment, to your touch. There are a lot of organic materials from in your hand, the assembly becomes difficult. So, it is a procedural problem. The die is very small and it is diminishing, as we have seen in various system applications. But in microprocessors today, the die can be large, but still they are very sensitive. IC package is some sort of a mechanical interface of the die and the environment, right. So, it prevents from damages during manufacturing, especially soldering, where a lot of heat will be involved and your first level interconnect cannot be disturbed or spoilt during the soldering process, which involves high temperatures, and also from normal day to day use after the device has been manufactured. You also prevents the you can prevent the die from electrical stress like electromagnetic compatibility or EMI, electromagnetic interference, from the system level printed wiring board, because you are going to use various other devices. Then if you are going to use, for example, expose it to UV light either during a programming like EEPROM or during the operation, if there is an exposure to UV light, then you can have electrical stress that can creep into the system and spoil your first level interconnects. Then X-rays like space conditions and avionic environment, these are areas where you can expect damage to the die. That is why it needs to be protected. So, the packaging requirement is speed is a major issue, which means chip to chip propagation delays should be shorter. The same holds good when you talk about interconnects at the second level printed wiring board. Obviously, this is a major consideration when you look at VLSI design. The interconnect lengths are very small. Then high bandwidth, pin count and viability is a major requirement. All IC manufacturers look at increasing the number of IOs per chip, thereby increasing the wiring density. And you need to reduce the size of the device, because today the product size is also reducing, and in between the board also gets reduced. This I have repeated time and again. One of the important packaging requirements today is that the thermal and mechanical stress needs to be reduced on the device. So, you should have a high heat removal rate, good match between thermal coefficient of expansion of the die and the chip carrier. So, the chip is a silicon and the chip carrier can be a plastic. They have different TCEs, that is the thermal coefficient of expansion. Therefore, how do you take care of thermal mismatch when you are using these materials? But at the same time, for such a device you need to use a plastic because it is economic. Prevent the die from destruction during such thermal flare ups that can happen during the powering up of the circuit. Then you talk about electrical test. You must be able to test the device or the package easily after it is packaged, okay? And then it should be highly reliable and of course low cost. So, chip mounting can be, as we have seen earlier, pin through hole. That means your package should have pins that should traverse through the PCB, and easy manual mounting. So, when you use a pin through hole format, instead of depending on automated equipments, you must be able to mount these devices like your dip package here, which is typically you can use this dip package and mount it on a printed wiring board, for which the holes have been manufactured, and you can use your bare hand to simply insert the device into the system level printed wiring board. Problem passing signals between pins on PCBs. Obviously, when you have pins, you cannot utilize the area on the other side of the printed wiring board. Therefore, you are losing the real estate, you are losing in terms of connection density or the pin density, and it is very difficult to pass number of lines between two such pins. There is a restriction on the number of routing pins. Therefore, the density is reduced. Then you can opt for surface mount device, because it has got a small footprint and it utilizes only the surface of the PCB rather than going through the PCB. So, typically this kind of package, the QFP or your BGA or your CSP, will be utilizing surface mount technology. Even your pin grid array here utilizes pin through hole technology like your dip package. Therefore, for this you require special machines required for mounting. The assembly technology becomes different. but there is no blocking of wires on the other PCB layers, because the pins do not block, there are no pins. The surface mount technology means the pins do not come to the other side, therefore, you get more area on the other side of the printed wiring board to route your tracks, and therefore, this kind of a format for chip mounting will result in high density. So, the types of single chip packages can now be classified as through hole packages, which is single inline package, dual inline package. They can be plastic. So, these are the materials that you can think about for these package types. So, through hole, it can be a plastic package or it can be a ceramic package. Okay. Then you have surface mount technology, where you have different types, and again the types of materials that are used are either plastic or ceramic. You have small outline package, leaded chip carriers LCC, quad flat pack and tape automated bonding tab package, which is again a surface mount methodology. Then the other classification is area array package, in which you get pin grid array and ball grid array. Here you can have plastic pin grid array, plastic ball grid array, ceramic pin grid array and ceramic ball grid array. Then you have another variety called column grid array. This is a particular methodology or package format which has got limited circulation, or you do not see this in high volumes, typically used in boards which are high dense in terms of requiring thermomechanical reliability standards to be very high, like in military applications and so on. And then you have finally the chip size package, in which you can have plastic chip size package as well as ceramic chip size package. So, the other two columns here will indicate to you the typical pin count or the total IO that you can probably see are available in the market today, and this also gives minimum pitch. So, you can see minimum pitch starts from 2.54 mm to something like 0.5 and lower than 0.5 today in terms of QFP 0.3 and so on. 0.3 is also available in BGA CSP formats today. So, you can see the range in minimum pitch as you go through this table, and also you can see the high pin count. Typically, you can look at even less than 48. Many of you would have seen 14 pin dip, or today you can see FPGA components coming in BGA format, which has got over 1700 solder balls, which represent the total IOs that need to be connected onto a printed wiring board. So, we will stop here for this particular class. What we have seen basically is the definitions for single chip module. We are going to see what a multi-chip module is in the next class, and we have tried to see how SCM or SCP can be classified based on assembly technology, based on materials and so on. And we have ended up looking at the important things like formats available and pin counts, and how relevant pitch is, that is the IO pitch is in deciding the package format for various types that we are seeing in the market today. Thank you.